And thank you very much to the organizers for inviting me to contribute here. I wish I could be there in person, but it's a bit difficult. We're starting our teaching very soon here in UCL. But I hope I still am able to get you excited about a couple of physical layer technologies for making wireless networks sustainable and multifunctional. And in this talk, I'm going to talk about mainly two things. One is signal processing at the transmitter to reduce power consumption for downlink transmission. And the second is integrated sensing and communication for multifunctionality. So as a bit of a motivation, the future generations of networks will have an infrastructure, a wireless infrastructure that is expected to support a number of services beyond next generation communication, to include localization from the network itself, imaging and environment mapping, security, incident accident detection, critical infrastructure monitoring, smart mobility, connected cars, and also gather data and build intelligence for the network itself, but also for the greater smart city ecosystem. At the same time, there's a big demand for future networks to finally start complying with some sustainability development goals. And in terms of 6G, here's a number of things I think that we need to pay attention to. So always improving energy efficiency towards a net zero operation at some point one day of the network itself, but also the network supporting net zero operation of other systems. A network that supports the environment and the health of the population, a network that is sustainable and allows financially and climate-wise sustainable growth, a network that is reliable, secure, and private, and that supports the resilience and robustness of society. And if you look at the wireless network, it's well known that the ICT sector consumes about 2% of the global CO2 emissions, and that is a significant number, similar to the aviation industry. And if you look at where this is consumed in the cellular network, here's a breakdown of energy, operational energy and embodied energy at the base stations and at the mobile units. And the two main things are the operational energy at the base station, and that for our purposes for signal processing relates to the transmit power, the power budget, the power amplifiers. And the second one is the embodied energy at the mobile. Embodied energy relates to the energy consumed in building a mobile. And that also relates to things like the complexity of the mobile, its architecture. And for us in the signal processing, that means the complexity. So the numbers of operations that the mobile needs to carry out. Now, beyond the above challenges, we have the current trend is towards an ecosystem where we keep putting more and more devices, more and more emitters in systems. And a classical example of this is the connected car. So the connected car is required to support a number of communication modes, such as vehicle to vehicle, vehicle to infrastructure, vehicle to smart grid, and a few others. And at the same time, do a lot of sensing. It will carry cameras, lidars, but also at least three types of radars: long, medium, and short range radar. And if you look at this growing population of devices for sensing and for communications, this is not really sustainable. At the end of their lifetime, these devices will end up in a landfill and become electronic waste. But even before that, growing the numbers of devices only puts pressure in terms of the chips required. And we've been going through a chips crisis over the last few years from the COVID times. So the two things I want to discuss is multi-access technologies to exploit interference as a useful signal power that comes for free, that is green, and multi-access technologies to enable the reuse of hardware through multifunctionality of the network, and that relates to integrated sensing and communications. So for the first part, so I want to talk about designing signals for reusing interference. And again, looking at the power consumption, I'm going to be addressing these two main elements. So the transmit power, so the energy efficiency at the base station, and the complexity at the mobile unit. Now, the concept of constructive interference is what I'll be exploiting. So I'm going to be reusing constructive interference that's already there in the communication system to improve the performance, and in that way, save and transmit power for a given performance requirement. Now, to characterize constructive interference, we need to look at the basic constellations. So here's an example of PSK constellations. If you look at BPSK, these are the two nominal constellation points, 1 and -1. This is your decision threshold, the imaginary axis. And any interference that pushes my signal away from the decision threshold is constructive. So all these green dots represent constructive interference. Anything that pushes me towards the decision threshold essentially reduces my signal to noise ratio and my tolerance to noise, and that's destructive. So the red dot over here. And you can extend this to higher order modulation, QPSK, and this is your constructive region, 8PSK, your constructive region. And you can do that for QAM and other constellations as well. Now, we've been working in this area, myself and my team, for about 15 years now, and we've been showing orders of magnitude reduction in the required transmit power for a given performance. And I'll be looking into this in a bit more detail, but the early works go back to 2007 and so. Now, how to characterize constructive interference? So if I look again, if you imagine this is the 1+J constellation element for QPSK, so I'm focusing here at QPSK, so this constellation point. I need to characterize constructive and destructive interference. So let me first, so this is my nominal constellation point. The green shaded area is the constructive region, and this is my received signal that I want to lie in the constructive region of the constellation. So first thing I want to do is equalize the phase of the constellation point here. And if you imagine all 4 constellation points equalized their phases, they all fall onto this point over here. And the received signal equalized by the phase of the nominal constellation point is this guy over here. And then with basic trigonometry, you can come up with mathematical criteria to make sure that your received signal is always in the constructive region. This is the rotated now constructive region. And it turns out, first, I need to make sure that the real part of this guy is greater than a given threshold, gamma. And this gamma can be shown to be essentially an SNR threshold. So increasing this SNR threshold means I'm moving further away from the decision thresholds in my constellation. So I'm improving the SNR. And the second thing is, for a given real part, the imaginary part will need to be within the constructive region, so within these bounds. And here's the math. And it turns out that the second condition already includes the first one. So this is really the only condition you need to obey. So this is now your criterion that makes sure that the received signal benefits from constructive interference. So I'm reusing interference that's already there in the system as a useful source of signal power. And as I said, gamma is an SNR threshold, and here it is. So gamma is the true SNR that I want to achieve. This gamma that I use here is a function of that. And you can extend this to QAM, as I mentioned. I'm not going to go into the mathematical detail, but if you look at the constellation, so these 4 corner constellation points, they're like QPSK constellation points. So you can push towards these directions by improving. So you can exploit interference in these directions and improve performance. The blue shaded areas, you can do the same only towards one direction of the constellation, because you have decision regions in these 3 directions. And then in the center, you have decision regions all over the constellation point, all around the constellation point. So in the naive approach, you cannot do anything about constructive interference. But of course, if you imagine that I'm exploiting constructive interference for all these guys, the outer constellations, I'm essentially expanding my constellation in all directions. That means that these decision regions can also expand. And that means that these guys can also benefit from constructive interference. But I'm not going to go into the detail. You can look at this paper if you're interested. Now, how is this useful? So once I have the criteria for constructive interference, and remember this is essentially an SNR constraint here that I can use, I can go into any classical optimization problem where I have an SNR constraint. And here are 2 very fundamental examples. So power minimization, I'm minimizing the transmit power subject to an SNR for every user in the downlink. And here I'm maximizing the minimum SNR that you users observe for a given power budget. so the dual problem. So take out the classical SNR constraint that treat interference as harmful, replace that with this kind of constraint, and here you go. So this is now your power minimization that exploits interference constructively. This is your what we call the SINR balancing, but now exploiting interference constructively. And as I said, there's many works on optimization in many types of fields, not just for the classical downlink, but cognitive radio, ISAC, full duplex, so many such optimizations. You can go into these, replace classical SNR constraints with constructive interference constraints, and now you have a more energy efficient transmission. So without going into more examples, I wanted to show you a couple of key benefits that this technology has. So the obvious one is that for a given performance, a given SNR, let's say, I can drastically reduce the transmit power I need to use. And maybe the best place to look at is this graph over here. So I'm plotting the transmit power that I need to use for a given SNR threshold using the power minimization approach. And here's the more critical, let's say, scenario, the symmetric scenario, where I have 4 antennas and 4 users. I'm using QPSK. And you can see that the classical power minimization achieves this transmit power, while you can drastically reduce the transmit power about more than 5 dB in this very small scale scenario. So as you go higher in the numbers of antennas and users, you get more and more performance benefit. And this happens just by reusing interference. So I'm not changing anything. I'm just changing the signals. I'm not changing the infrastructure. I'm just reusing interference that's already there in the downlink transmission. So that was the obvious gain. Now, another gain that comes with this is that I have improved feasibility of designing these precoders, and that has real gains in terms of accommodating users in a given cell. So if you look at this graph here, this is the probability that this optimization is feasible. That means gives me a good, a reasonable SNR for a given power, with increasing number of antennas at the base station where I have an N by 4 system. So N antennas, 4 users. And the best way to look at this is starting from 6 antennas, 4 users. Both conventional and constructive power minimization are feasible. I reduce down to 4 the symmetric system, so they're both feasible for a Rayleigh channel. But then when I have 3 antennas, 4 users, conventional precoding is no longer feasible. I don't have the degrees of freedom to accommodate 4 users with 3 antennas. But because I'm reusing interference here, that means I can use that interference to modulate information and accommodate an extra stream. So 90% of the time, I can serve 4 users with only 3 antennas, so more users than antennas. Half the time, so 0.5 here, half the time I can accommodate 4 users with only 2 antennas, and 10% of my time I can accommodate 4 users with only 1 antenna. And if you look at the optimization, this is because classical optimization, so classical power constraints, SNR constraints, will basically constrain your received signal inside a circle or some hypersphere around the nominal constellation point, so highly constrained optimization. While constructive interference opens up the region, semi-infinite regions towards these 2 directions, so a lot more relaxed optimization. So this second benefit is the fact that it can accommodate and superpose more users than antennas. A third benefit is the fact that constructive interference precoding, it also goes by the name symbol level precoding, because it depends on the symbols that I'm transmitting. And that means the SNR constraints that I have are instantaneous. So while conventional power minimization, shown again here, will have these average constraints or ergodic constraints, so there's no data here. So once you have this SNR, so that's your constraint, but in the real transmission, you're going to multiply your precoder with the data, right? And that means depending on the combination of data, the addition here of the interferences can add, again, constructively or destructively. And that means that interference might violate this SNR constraint here. And this is now the SNR you actually achieve. So once you measure it. So here I'm using an SNR threshold of 20 dB. And you can see most of the time I'm achieving 20 dB. Some of the time I'm achieving better, because I have this constraint, but when I multiply with data, it's actually constructive, and I have this benefit. But some of the time, I have destructive interference here. So the SNR I actually achieve on an instantaneous basis, so multiplying this with the data, is less than the threshold. And in a real system, that will lead to an outage. So if you tell me my mobile unit needs 20 dB to operate, and I'm only providing 18 dB, that's an outage. Well, for this interference exploitation, because data is here, so these are the information symbols, that means I'm always achieving the 20 dB or greater. So there's no outages in such systems. And now the one main drawback of this approach is, as I said, is symbol by symbol. So that means I have to define the precoders on a symbol by symbol basis. While in classical beamforming, the beamforming here is only a function of the channel, right? Not the data. Here, the beamforming is a function of the channel and the data I want to transmit. So that means an increase in the complexity at the base station, at the transmitter. But what happens at the receiver? So at the receiver, in a classical, again, approach like power minimization, you can see here, the SNR constraint involves this composite channel. And that means at the receiver, I need to equalize this channel. That means I need to know this product here and equalize it, and then I can do my detection, right, in the constellation. So this knowledge means either that the base station needs to feed forward the channel estimates for the composite channel, and so on. And that is subject to quantization errors, it's subject to reception errors, it introduces overheads in my transmission, or this guy needs to do its own channel estimation and try to somehow find out what beamformers this base station is going to use, but that needs a lot of signaling exchange. So it's even less practical. While here for constructive interference, because I'm now forcing interference to lie in the constructive regions of the constellation, that means I can take my received signal and directly do my symbol decision, right? So my symbol is here, I can always get it right? I always know that it's going to be 1 plus j, nothing to equalize. That means this guy can operate without knowledge of the channel. There's no need to feed forward. There's no need to quantize. There's no need for this guy to do any complex channel estimation. So you can see here how by sacrificing some extra complexity at the base station, where you typically have the more resources, I can reduce the complexity at the mobile unit, while at the same time having all these benefits that I just discussed. So we have been playing around with this in our lab just to convince ourselves that this works over the air, the constructive interference. And here's a setup. So this is a blueprint of our lab. We emulate an access point with 6 antennas using USRPs, and 2 users, 1 antenna each, placed close together, so we have a highly correlated channel, so we have a lot of interference between the 2 users. And we use a technique called SCFDM, so it's an OFDM transmission where you squeeze the subcarriers in the spectrum, so you have non-orthogonal subcarriers anymore, so you get this interference between the users. And here's the results that you get without any precoding. So we're transmitting QPSK, and this is what we receive, a blurry constellation. With 0 forcing precoding, we're taking care of this interference between the subcarriers. And you can see here now more concentrated dots around the constellation points. And this is with constructive interference. You can see how the constellation is being spread in all constructive directions of the constellation. So we've shown this in our lab, and it works over the air. And there's been a lot of effort from ourselves and other teams trying to reduce this complexity and address the main drawback, which is the complexity at the transmitter. One of the more recent ones has been using data-driven approaches, so model-based data-driven approaches, where the approach is to take the power minimization that I've been showing all through this presentation, come up with an iterative solution, and we use the Lagrangian here to come up with an iterative solution, and then unfolding the iterations into a neural network where each of the layers represent an iteration. So this is using deep unfolding. And then that allows you to parallelize processing and reduce the computational time. On top of that, we've been looking at quantizing the neurons of the network in our implementation, either binary quantization, 1 or -1, depending whether the weights in the neural network are positive or negative, ternary, 1 and -1, or 0 when they're very small, and also stochastic quantization. So we take the neural network and quantize some of the elements, and by quantizing a given percentage of the elements, you get a trade-off between the performance you achieve, because you lose some of the performance, but gain in terms of complexity, memory consumption, and so on. So I only need 1 bit here to represent these numbers, while these numbers typically we use 8 to 12 bits to represent. So with this, we've been able to come up with complexity performance trade-offs, and here's the transmit power. Here's what conventional power minimization uses, so treating interference as destructive. Here's what you use without any quantization, so full precision, a neural network approach, so about 4 dB gain. And here's a graceful sacrifice of the power savings as I increase my quantization, so as I reduce the complexity and the memory consumption in my neural network. And with this, you can get a very flexible trade-off between the model size, so the memory consumption, the bottom line performance, so the power that I'm consuming, and the computational complexity. And you can see here from the full precision network, which achieves the best power efficiency, I can gracefully trade off this power efficiency to get the optimum model size and complexity. And this has been very useful in NOMA systems. So NOMA is a technique that is being examined for the standards. Now NOMA suffers from, so NOMA works by superimposing multiple signals in a single resource. And here's an example where I superimpose 2 users per beam from the base station. So I allow them basically to interfere, and I can resolve them in some domain, for example, the power domain and so on. Now, what NOMA suffers from is from the need to cancel interference on a symbol by symbol basis at the user, right? So the interference from user 2 here acts as interference to user 1 reception. So I need to cancel that, and I need to do it symbol by symbol. And that means I need to, again, estimate the channel of both users and the user that I'm canceling interference, and do these extra computational overheads. Now, the idea here is to make this superposition constructive, and in this way, I'm saving in complexity, I'm saving in energy efficiency, and I'm also saving this need to do successive interference cancellation. And in fact, I get better performance. So for perfect successive interference cancellation, the first user here that is canceling interference will get single user performance. The second user will get this kind of performance. So this is basically the minimum between the rate that the 2 users can achieve. And why is that? It's because both users need to decode the the signal of user 2, because user 1 needs to cancel that signal to get its own signal. So that's actually less than the space division multiple access. Well, once you apply the principles of constructive interference, so both users basically achieve single user performance or better. So here, the user that suffers interference from the other user, user 1, actually benefits here from constructive interference. So better than single user performance. While user 2, I do nothing about user 2. So they actually have the performance of SDMA. So you can see here, but by applying the principles of constructive interference, I'm saving in power consumption, I'm improving performance, and I'm also reducing complexity at the mobile unit. So I'm removing this need to cancel interference on a symbol by symbol basis. So estimate the signal of this user, cancel that signal, and then do my own estimation. And here are some performance results. So the obvious one is the saving in transmit power. So you can see here that constructive multiple access, so COMA, has a reduced power consumption. It has an improved symbol error rate performance also with respect to NOMA and orthogonal multiple access. And the real benefit is in complexity. So here we've calculated complexity, and you can see here about 1/3 of the complexity of NOMA. And that is focusing only on the complexity, but don't forget, again, I need to estimate CSI, I need to cancel interference, and that's subject to errors on its own. I need to quantize CSI, and so on. So this is a true breakthrough, I believe, for NOMA and rate splitting multiple access techniques. And if you're interested in these, feel free to take a look in some of the works. So the early works on constructive interference, some good overviews that are out there by now. How this is used for beamforming, how this is used for hardware constrained approaches like constant envelope precoding or hybrid analog digital precoding. Some massive MIMO works, some works on closed form solutions, again, to reduce complexity that I didn't have the chance to present here. And there's our work in experimenting with this over the air. But we've also applied this in other domains. So this is the two papers that describe this deep learning based approach. You can apply this, as I said, to full duplex communications and treating self-interference as a constructive source. You can apply this to security, and we'll see a short example in a minute. You can apply this to rate splitting, to communications and radar and multi-cell approaches. Now, the next thing I want to discuss is the concept of multifunctionality. So again, incorporating sustainability through reusing hardware, so not populating more and more devices, but reusing the existing infrastructure, the communication infrastructure for sensing. And if you look at all these services that I spoke about early on in the talk, they boil down to two fundamental functionalities: communications and also sensing. So localization, imaging, detection, connected car relies on sensing. And sensing is now the new functionality that we're trying to address in the cellular network. Sensing is highlighted as a key usage scenario in IMT 2030, basically 6G, and also along with integrated AI and communication. And what better way to gather data and build intelligence if not through sensing? So I argue that integrating sensing and communication not only addresses this new use case of 6G, but also the AI use cases. And now the integration of sensing and communications is a step ahead from their previous coexistence. And in fact, that so you're moving from systems that compete for resources to systems that are co-designed. So I'm co-designing now a signal, a waveform, a transmission that does both things at the same time. Communicate information to a user, while the same transmission, the same signal can be used to detect a target. And if you think of this being deployed widely in the 6G network, every access point being a small radar, that gives you the opportunity of coordinated sensing of an unprecedented scale. So perception and awareness of an unprecedented scale, with infrastructure that's already there, just changing the signaling. Now, in terms of signaling, we have three types of signals that enable dual functional radar and communications. The first one is what we call the radar-centric design, and the main principle is this one. You take a radar waveform, you somehow modulate information onto that waveform, and then you have a dual functional waveform that does both radar while also conveying information. The most popular way of doing that is using index modulation. So using indices and parameters of the radar waveform to convey information, and I'll show you an example in a minute, but there are other ways like side lobe signaling and so on to convey information. The counterpart of that is what we call the communication-centric design, where you take a communications transmission, use that as your reference signal for detection, and then you have this dual functionality through your communication signal. And this is similar to passive sensing. And again, there's many techniques in terms of using the data payload for sensing, or some key elements in the frame, like the reference signals, which are known for the good autocorrelation properties, and using them for sensing. Now, radar-centric design is great because you can take any operating radar and change small things in the signaling, and then you have dual functionality. But the limitation here is that you can never achieve, the gigabits per second that you need for communications. It's very difficult to achieve those with index modulation. The communication-centric design is great because it's very close to the standards, minimal changes in the the standards and the frame, the communication frame and the standards, and I have my radar detection. But again, it's limited in terms of the sensing you can achieve, and it's very difficult to scale the sensing. So that's the performance I can achieve, similar to passive sensing. And it's very difficult to achieve better performance without introducing latency, using more frames, and so on. And that's where the jointly optimized design comes in, where you design signals from the start to operate all the way from radar only transmission when you have radar critical applications, communications only transmission when you have the communication critical operations, but anywhere in between. So a flexible trade-off, which allows you to achieve your gigabits per second when you need them, but also the very reliable radar detection when you need it. So just to look at a few examples. So this is one of the very early approaches in doing that back in 2018. So where we're trying to design a signal that can convey information to these communication users, while the same signal can be used to detect a target. And if X is the signal I want to design at the baseband, anything that lives inside the H times X, so the channel times X, that is not the signal, the information signal S, anything that lives inside here is multi-user interference, and I want to minimize that for communication purposes. And then for radar, I want to come up with a waveform X that is close to an ideal radar only waveform. So if X0 is the radar waveform, the ideal radar waveform, I want the distance to that waveform to be small. And you can come up with these weighted optimizations, and now you have a signal that is designed dual functional from the start and with a flexible trade-off. So here I have a weighted minimization of the multi-user interference and the distance to an ideal radar waveform, subject to constraints. So here's a total power constraint. You can have per antenna constraints, you can have constant modulus constraints, PAPR constraints, and all kinds of other hardware-informed constraints. Now the key parameter is the weighting factor. So when rho is 0, this guy goes away. I'm putting all my priority onto radar. When rho equals 1, this guy goes to 0. I'm putting all my priority into communications. And when rho is anywhere in between 0 and 1, I have a flexible trade-off between communications and sensing. And here's a snapshot of that trade-off. I'm plotting radar probability of detection against communications achievable rate. And here's now the trade-off. So rho equals 0, I'm doing radar only. So you can think of this as a radar-centric approach, where I get my good probability of detection with some communications rate. Rho equals 1 will give me my communications priority. You can think of this as passive sensing. I do my maximum communication rate, but with a poor probability of detection, a bit better than a random guess. But now with this weighted optimization, I have all this regime here that I can explore. By tuning rho, I can achieve any of these points in between. And this trade-off becomes more and more benign as I increase the degrees of freedom, for example, the number of antennas to the number of targets and users. And you can see here a system with more degrees of freedom where I can achieve the good communication rate with a much better radar performance, so a much less sacrifice in the radar performance. And again, this is something we tested in our lab. So this is our communications lab in UCL. Again, the access point with 6 antennas, 2 communication users. And for radar, I'm assuming there's a direction I want to search. I'm forming a beam towards that direction, and I'm measuring that beam with this directional antenna over here by moving it around. And with that, I can observe the communications versus sensing trade-off over the air. So here I have a QPSK constellation that I receive at these users. And here I have the beam pattern I can achieve for radar. And here, when I put all my priority on communications, I have a nice clean QPSK constellation, but very little in terms of beam forming. I put all my priority in radar. I have a nice clean beam for my scanning, but a very blurry constellation. But I can also move anywhere in between where I have a good compromise. For example, here, I have a good enough constellation with some sort of beam forming. So again, the trade-off between communications and sensing over the air. And we've been able to use this beam for radar while talking to these users to do people's counting. So detecting basically when something obstructs my radar beam. And we've been able to get good probability of detection with good probability of false alarm. So again, a true sensing application, so a people's counter, while at the same time I'm communicating to users. Now, in terms of the radar-centric design, so here's another experiment in our lab. This is our radar lab now. So we have our radar transmitter and receiver. This is our target we want to detect, and a communications receiver. And here we're using an RF system on chip platform, where we're able to produce flexible radar waveforms. So we take an LFM waveform, basically a chirp, and now we use index modulation with these three indices. So the center frequency of the waveform, its bandwidth, and the polarization of our transmission. And with these indices, we can come up with a communication constellation, and it's actually 10 bits per symbol that we can achieve. And this allows us, again, to convey information with the radar waveform and to come up with trade-offs between sensing and communications. And the trade-off comes by tuning the pulse duration, the radar pulse duration. A long pulse duration means I have a good radar performance, so I have a high integration gain for the radar, and that gives me a better radar SNR. So here's the chirp duration. A short chirp duration means I have more of these chirps that carry information per second, and that increases my communication throughput. So by increasing the chirp duration, so the minimum chirp duration will give me my maximum throughput. Start increasing that, I have a graceful degradation with my throughput, but I get a better radar SNR because the pulse is wider, so I have an integration gain. And you can see here the clear trade-off by trading off the throughput to improve my radar SNR. And you can see here we're taking this to field trials where we're detecting a static target and a moving target. And you can see, again, by reducing the chirp duration, this graceful degradation where I start losing the moving target once I have a very small chirp. And my priority is in communications. Now, the final thing I want to discuss is the unique security threats that I think ISAC holds. So integrated sensing into communication networks is a very useful functionality. It will unlock a lot of services that the network will need to support. But I think it also introduces some entirely new security vulnerabilities. So the first one is the one relating to data security. So if you look at this scenario here that we've been looking at all along, so a dual functional base station communicating to these guys and with the same signal trying to detect a target. Now, ISAC means that this probing signal that I'm using for the target will also carry information that is intended to these users, right? It's the same signal. And that means I'm opening up the opportunity to the target to act as an eavesdropper and try to eavesdrop the information that is intended for these users. And the target will do that with a lot of signal power because I need to illuminate the target with a lot of power here, right? And the target can be, a friendly, let's say, node that is cooperative in terms of being sensed, but it can also be a non-cooperative node, like a non-cooperative car. It can be a UAV, a malicious UAV that is trying to eavesdrop information, but it also can be an enemy aircraft in a military scenario. So there's many scenarios where you don't want this to happen, the target being able to eavesdrop information. And you can encrypt the data so that this guy cannot extract the data. But even if it's able to detect that there's a communication link, or even detect the bandwidth that is being used, or the center frequency, or the location of the base station, that is critical information. In some of these scenarios, you don't want to jeopardize that information. So physical layer security is definitely relevant here. And now the key challenge in applying physical layer security, there's many solutions in over the decades of physical layer security that have happened so far. The key challenge is in the radar link. So as I said, I want to illuminate the target with a lot of signal power, but I also want that power not to be useful for the target to use for eavesdropping. So at the same link, at the same direction, at the same time, I want to get a good radar performance, so a signal direction, I want to limit the eavesdropping SNR of the target that it can use to eavesdrop the information. And that excludes a number of families of physical layer security. So you cannot do node steering, which is a classical solution. So steer nodes towards the eavesdropper here, because you want to illuminate the target for a good radar performance. And I need to obtain these two SNR constraints while at the same time giving a good quality of service to the users. So good SNR for the legitimate users. So that means I want to push a lot of power towards the target, but that power not being useful for detecting information. So you can apply artificial noise designs, so where you push a lot of power here, but it's mainly noise, and we've done that, and you can again achieve trade-offs between the secrecy rate now, so the data security performance, and the radar peak to side lobe ratio, so how well I'm designing my radar beam pattern, so essentially the radar performance. Again, by tuning the optimization, you can get this graceful trade-off where from the maximum security, when I start prioritizing the radar performance, I have a graceful degradation of the security and vice versa. And another approach here is again exploiting interference. So as the first step, we've been experimenting with exploiting subcarrier interference. So again, if I take you to this notion of spectrally efficient FDM, so taking OFDM and squeezing the subcarriers so that they take up less bandwidth, you can see here they're non-orthogonal, so the interference from this guy will interfere onto this subcarrier, and I'm going to exploit that interference for security. Now the key parameter here is the compression factor. That tells me how much I'm compressing the spectrum, so how much I'm squeezing the subcarriers, and how much interference essentially this guy is going to cause onto this subcarrier. We've been using this together with our colleagues in UCL to improve spectral efficiency in classical systems. I want to use it here for security. So let's take this scenario where you have a NISAC access point communicating to these two users, detecting a target, and I have here a presence of an eavesdropper that is close to one of the users, so a highly correlated channel where I cannot do, again, node steering or rely on the randomness of the channel to hide my data. So first of all, by designing these signals that I've been talking about, you can do this trade-off between sensing and communications. But now let's see what happens when I have an OFDM signal or a spectrally efficient FDM signal. So in the OFDM signal, I have no interference, and that means this is my access point. These are my two users. If the eavesdropper is close to the legitimate user, so a highly correlated scenario, the received signal they're going to observe is similar. So that means the constellation of the legitimate user and the eavesdropper is going to be similar. So if I have a clean enough constellation for the user, I have a clean enough constellation for the eavesdropper. So the eavesdropper in this case can eavesdrop the data. Well, for SCFDM, I have this interference, and that means at the receiver, I need to equalize this interference. So if the legitimate user knows the compression factor I'm using, it can equalize the interference and get the constellation. While at the eavesdropper, in the absence of this knowledge, I get a very blurry constellation. So again, a degree of physical layer security by exploiting this intercarrier interference. And you can go one step further in exploiting this interference that I've been talking about in the first part of the discussion, where I can use both constructive and destructive interference to protect against eavesdropping. So again, the idea is to use these kind of criteria and push the signal towards the constructive region for the legitimate users. Well, in this scenario, where I have the users and the target being my eavesdropper, so the users will benefit from constructive interference. I want the target to be harmed by destructive interference. So make it difficult for the target to detect the data by pushing their signal in the destructive region of the constellation, meaning it's going to get the detection wrong. So here's another optimization where I'm maximizing the radar SNR, so the minimum across all the directions I want to illuminate, while ensuring constructive interference for these users. So these guys are going to benefit from the constructive interference. The target acting as an eavesdropper is going to be harmed by destructive interference. And this is what you get. So again, QPSK, I'm transmitting 1 plus J. this is what the legitimate user is receiving. So the blue dots here. So all in the constructive region means the user will get it right, the detection right all the time, while the target is getting a random signal across all the directions. In this case, I'm only using constructive interference. I'm not doing anything about the eavesdropper. So you can see here, the users will always get it right. The target acting as an eavesdropper will be basically a random guess of what is being transmitted. If I now exploit destructive interference for the target, again, the user will get it right. The target is always in the destructive region of the constellation. So in this sense, the target will always get it wrong. And that means, looking at the symbol error rate with increasing SNR, all users will have a degrading, so a reducing symbol error rate with increasing SNR, as they should have, while the target here acting as an eavesdropper, this is the constructive only case, will get it wrong 3 out of 4 times. I'm using QPSK here, so 3 out of 4 times the target will get it wrong. And you can push this symbol error rate to 1 if you apply destructive interference. And all that happens while I'm still able to achieve a good beam pattern for radar detection. So I'm still pushing a lot of signal power to the target, but this power is destructive for the decision, for the detection of the data, and that's how I achieve security here. Now, the other big vulnerability, and that's something we never had to worry about in a cellular system, is securing against adversary sensing. So if you think about this, infrastructure in a few years' time from now, where everything is tuned for ISAC, so the base stations, the signals, the network, the geometries are tuned for sensing as well as communications. That opens up the opportunity for unauthorized devices to do their own sensing. So exploit these signals that are now tuned for sensing with passive sensing on their side to map the environment or detect targets and so on. So again, I have an unauthorized node that is exploiting this infrastructure to do its own sensing. So in addition to data security constraints, I now have the very important sensing security constraints. And these are very difficult because there's no data to encrypt. That means I cannot do anything in the higher layers. I cannot encrypt anything. It all has to be in the physical layer. And oftentimes, I don't know what I'm protecting against. I haven't had a good detection of the target myself to be able to protect it against sensing. Now, here's an initial bit of work that we've done in this area. So a more specific scenario. So we have a scenario where a dual functional base station serves a number of communication users, while at the same time providing sensing services and localization services to a target through a bistatic link. So this is the legitimate radar receiver, another base station that is basically determining the location of the sensing user, while I'm also serving communication users. Now, one of these communication users that's only authorized for communications, not authorized for sensing, is trying to act as an eavesdropper and sense the environment. So also localize this target. And I want now to protect my target from being sensed by this unauthorized sensor. You can build up another optimization here. So what we've defined is the radar mutual information for the legitimate receiver and for the eavesdropper. And by defining these radar mutual information, so the sensing performance essentially, you can build up optimizations where you maximize the radar performance for the legitimate radar receiver, while constraining the mutual information, so essentially the information that this guy can extract from the target to be less than a threshold, again, subject to the usual constraints, so the total power constraint, the SNR constraint from the communication users, including this communication user, and other constraints that relate to the optimization. And you can do the same by adding extra degrees of freedom in the form of artificial noise. And here's now how you build your optimization. And what this effect has is now I'm looking the mutual information, the radar mutual information with increasing transmit power budget for the legitimate radar receiver and for the eavesdropper. And if I do nothing about sensing security, this is what the eavesdropper gets, a very high mutual information. If I protect now against illegitimate sensing without artificial noise and with artificial noise, I can get these big gaps between the eavesdropper and the legitimate radar receiver, so up to 19 dB here. So a big gap between what the legitimate user can achieve, the legitimate radar sensor, and what the eavesdropping sensor can achieve. And again, you can build tunable trade-offs between the sensing security now. So here I'm plotting the mutual information gap between the legitimate user and the eavesdropper with respect to the communication SNR, so the sensing security against the communication performance. Again, a graceful trade-off where I have the maximum sensing security when I put priority on security, and I have a graceful degradation of security once I put more priority in the communication SNR, and that can be tuned by tuning the optimization with artificial noise, without artificial noise, and a much better sensing security compared to the baseline where I do nothing about securing against sensing. And the final thing I want to talk about is an opportunity for security that the sensing operation opens up. Now, a big limitation for physical layer security in the past has been the need to know something about the eavesdropper, its direction, its channel, or something about the eavesdropper. Now, the sensing that is incorporated in the ISAC network opens up the opportunity to actually sense things, map the environment, and detect potential eavesdroppers. So this information that I need for the eavesdropper can now be provided by sensing. And here's an example where we try to exploit this. So here we have a scenario where we have a communication-only system, but we use sensing to detect eavesdroppers in the scene. So I'm trying to serve these guys, but also protect against eavesdroppers. So here the sensing is used not for sensing itself, but to support the secure data transmission to the users. So this is a synergy where the sensing is used for the communication bottom line performance. So how we do that is first we want to detect the presence of eavesdroppers. So there's a sensing only transmission where we maximize the Fisher information subject to a total power constraint. And this is what we get. So this is the radar return for all these directions. So here the green lines are the communication users, and I know where these guys are. They're part of my network, in which directions. The blue lines are the estimated directions of the eaves. The red lines are the true directions of the eaves. So with these estimates, I can now come up with directions for the eavesdroppers. I can come up with channel models for the eavesdroppers that will have a certain error. And that means I can now, in stage 2, do a joint weighted optimization of my sensing performance, so the Fisher information, and the secrecy rate performance, so the secure data transmission. And that can be subject to a good radar beam pattern, which is given by these expressions over here, and a total power constraint. Now, the key here is that the secrecy rate is going to be a function of what I know about the eavesdroppers. So I'm going to have an estimate and a certain variance around that estimate. And that's going to give me the region that I want to protect against in terms of eavesdropping. And as I keep running this optimization and improving my sensing performance means the estimated direction will be closer to the true direction. And that means I'm going to have smaller errors in my estimate. That means I'm going to have a secrecy rate expression that is more accurate, that describes the real situation more accurately. That means I'm going to be able to improve the secrecy rates. That means I'm going to have more degrees of freedom to put into the sensing and further improve the sensing. And you can see here how these two functionalities mutually benefit each other. So improving the sensing functionality, sensing the eavesdroppers, will improve my secrecy rate for the users. And this mutual benefit is shown here. So first of all, the beam pattern and how it evolves as I improve my sensing performance. Originally, I have here the two eavesdroppers. First, I do an omnidirectional scan. So I scan the horizon for any eavesdroppers. Once I get a certain estimate of these eavesdroppers, I form a beam to cover both of these eavesdroppers. And as I further scan the environment, I have a better understanding of where the eavesdroppers are, and I can form a thinner, so a more focused beam pattern towards this direction. And that means I'm going to estimate even better. Estimating even better means I'm reducing the CRB of the amplitude and the angle of detecting the eavesdroppers. But estimating better means I'm improving the secrecy rate, so the secrecy performance, because I'm improving the model of the channel, of the eavesdropper, and so on. And that means with the iterations, with increased iterations, I'm improving the sensing performance, and that means I'm also improving the secrecy rate. And on top of these mutual benefits, which are achieved here in this example with rho equals 0.5, so this weighting factor equal weighting to the sensing and to the secrecy, I can also build in trade-offs in these where I tune rho. So a high rho gives my priority all the way to sensing, and you can see that this is going to improve much faster. And rho, a small rho, will give priority to secrecy, so protecting against eavesdropping. So again, you have flexible trade-offs between the data, secrecy, and the sensing performance. And with that, I'll stop here. And I hope I've convinced you that, despite all this excitement against Isaac and enabling sensing the pseudocellular network, there's real security challenges that we need to address before we deploy Isaac systems in reality. If you're interested to read further on Isaac, we have this book on integrated sensing and communications with my esteemed colleagues Fan Liu and Yonina Eldar. If you're interested to engage with the various Isaac communities, so there's this emerging technology initiative on Isaac. There's this Etsy group on Isaacs on pre-standards contributions. There's a technical working group on Signal Processing Society. And recently, we have established a NATO group and looking at defense applications of integrated sensing and communications. I'll stop here, acknowledging the team of people has been working in these areas for the past few years and the funding that has made this possible. And I'm happy to take any questions that you may have.
Thank you, Christos, for a very nice talk. Let's see if we have any questions from the audience. You have. So, Christos, you can hear us?
Yeah, I can hear you, Hamdi, but I'm not sure if I'm going to hear the question, so you might have to repeat for me.
Yeah, I have a question. Two questions. The first one is about the constructive interference.
Mm-hmm.
The first part of your presentation. So you assume that there's a small number of antennas, right?
So in the simulations that I showed, we typically use small numbers of antennas, yeah.
So interference means the inter-antenna interference, right?
So the interference that we're addressing here, so it's the inter-user interference. So the users in the downlink, let me see if I can find some sort of, so for example, in this experiment we have, so the base station, this guy is going to transmit to these two users. The signal intended for user one is going to be interference to user two and vice versa. So that's the multi-user interference that we're trying to address.
The second question is about the DFRC, dual functional radar communication.
Yeah.
You talk about the three designs, the radar-centric, communication-centric, and the joint design. I have a question on joint design. What kind of waveform is used for this joint design?
So the joint design, I mean, for this example that I showed here, the design is the baseband representation of the signal. So you can think of this as a precoding design, and this can apply to multiple waveforms. So for example, here in this experiment, we're using a narrowband IoT framework. So that's basically an OFDM that I think has 12 subcarriers. But I believe the same principles can be applied to other waveforms, like OTFS and all the other waveforms that are now being examined. So we're not really, in the early works, we called it waveform design, but what we're actually designing is the signaling the pre-coding, you can think of it.
So the waveform is more like a communication. Like because you use the OFDM or
so as I said, I mean, this applies to OFDM. So our experiment was for OFDM because we have a communication kind of, setup here in our communications lab. But you can do the same with a radar waveform. You can do the same with an OTFS waveform. It's just about changing the pre-coding. So if you have a MIMO radar, again, you can design pre-coding for that.
Thank you. Thank you very much.
Thank you.
Any other questions from the audience? So, Christos, I had a question. With the constructive interference, can you maybe say something about CSI at the transmitter? Because you talked about how CSI is not needed at the receiver, but I guess to implement any of this kind of stuff, you need to have CSI at the transmitter, right?
Correct. And it's the similar requirement for any kind of pre-coding, right? For any kind of pre-coding, you need to know the channel here, right? And do the pre-coding. Perhaps it's intuitive to think that once you're doing this symbol dependent, it might be more reliant on having a good estimate of the channel. But we have done studies on this. So studying the effects of increasing channel estimation errors onto symbol level precoding and classical precoding, and we've seen that in fact the trends are very similar. I don't have the figures here to show, but we have figures on robustness of these techniques. So similar to classical beamforming, you can do robust beamforming for constructive interference as well. So taking into account channel estimation errors, ensuring constructive interference for worst case channel errors, and so on. So you can do these things for constructive interference. And again, the trends you get in terms of performance are similar. In fact, again, you get these power savings. And you can see that, for example, when I start increasing my channel estimation error, so the error bound in a bounded error, you can see the transmit power shooting up, right? When I'm precoding for the worst case user. And this happens much earlier for classical beamforming and much later for symbol level precoding. So in these critical SNRs and in these critical estimation error regimes, again, you can get a lot of power savings for constructive interference.
Okay, thanks. I think we have a question online. Okay, there's no more questions. All right, if there's no more questions, then let's thank the speaker one more.
Thank you very much for the kind invitation. I wish I could be there with you. Japan is on my list, and hopefully one day I'll make it and work with you.
Great. Thank you very much, Christos, for the contribution, for the great talk.
Thank you.